Today I'll present second lecture of this series. Um, so I have already uploaded this lecture on YouTube. So if you don't regularly visit it, please go there. If you have any question, please post a comment. So let's begin. These are the contents of my today's lecture. But before I begin, let me give you a brief introduction about what exactly kinematics is. A manipulator can be schematically represented from a mechanical viewpoint as a kinematic chain of rigid bodies, which we call links, connected by means of revolute or prismatic joints. One end of the chain is constrained to a base, while an end effector, which can be a gripper or something like that, is mounted to the other end, which is the last leg. The resulting motion of the structure is obtained by a composition of the elementary motions of each link with respect to the previous one. Okay. Um, Therefore, in order to manipulate an object in space, it is necessary to describe the end effector position and orientation. So, in this study, we will study the derivation of direct kinematics equation through schematic general approach based on linear algebra. This allows the end effector position and orientation, which we call force, to be expressed as a function of the joint variables of the mechanical structure with respect to a reference frame. Uh, I present both open chain and closed chain kinematic structure. So, but for the time being, I'm only considering open chain. So let's begin. Okay. A rigid body is completely described in space by its position and orientation. And orientation, we call orientation as a pose with respect to a reference frame. You can see this is a reference frame as shown in this figure. So let O, which is called the origin, X, Y, Z, be the orthonormal reference frame, and X, Y, Z be the unit vectors of the frame. I would like to mention here that orthonormal vectors are the vectors which are perpendicular to each other, and their norm is 1. It is also worth mentioning that vectors and matrices are represented by bold letters like this one. Okay, so this is the orthonormal reference frame. Now the position of a point O dash is here on the rigid body with respect to the coordinate frame O x y z in this frame is expressed by the relation O dash, this is a vector, O x dash x, which is a unit vector, O y dash y, and O z dash z, where O x dash, O y dash, O z dash denote the components of the vectors, vector O, along the frame axis, this one. Okay. The position of O dash can be compactly written as 3 cross 1 vector in this form, X dash, Y dash, and OZ dash, in order to describe the rigid body orientation. So the point is orientation. It is convenient to consider an orthonormal frame attached to the body and express its unit vectors with respect to the reference frame. So what we are doing is, this: we are attaching a frame on this point, and we are going to represent its unit vectors like z bar, x bar, y bar with respect to this frame. Let then O dash origin of that rigid body x bar, y bar, z bar be such frame with origin in O dash, and x bar, y bar, z bar be the unit vectors of the frame axis. These vectors are expressed with respect to the reference frame, which is O x y z, by the equations like this. So you can see that x bar is actually represented by x bar unit vector x in x direction, x bar y, x bar y in direction of y, and x bar z in direction of z. Okay? And in the similar way, we have this equation and this equation. The components of each unit vector are the direction cosines of the axis of the frame bar x bar y bar z or dash with respect to the reference frame of axis. So these components which we are representing are actually describing the force. Now here is an important point is that we are not discussing the trans this distance from this origin. We're only considering the pose. So we are representing these axes with respect to these axes. Okay. So by adopting a compact notation, the three unit vectors in the previously described equation 2.2, which describe the body orientation with respect to the reference frame, can be combined in 3 cross 3 matrix. So x bar, y bar, z bar. We put these unit vectors here, 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 and we write it like this. Okay. So x is a unit vector, y is a unit vector, z is a unit vector, and this is again a unit vector. So if we write this x bar in this form, okay, and we see that x is I represent this x as like a vector like this, and y like this. So I'm gonna get this. So what we call with this matrix, we call this matrix as a rotation matrix, and that's it. What we are doing actually is we are attaching a frame over a rigid body, giving giving it some axis, a frame of axis like x bar, y bar, z bar, and then these unit vectors are going to be represented with respect to this frame. So representing these unit vectors with respect to this is called in the way by representing these unit vectors with respect to this frame, these unit vectors is known as is represented by using rotation matrix. So we are representing these unit vectors with respect to the base frame, and when we represent that, we call this the rotation matrix we obtain by using this we call that the matrix we obtain by doing this is called rotation matrix. Now, it is worth noting that the column vectors of matrix R are mutually orthogonal. Orthogonal means they are perpendicular to each other since they represent the unit vectors of an orthonormal frame. Okay. Again, I said they are representing the unit vectors of orthonormal frames, so this is going to be orthogonal, and that is if you multiply the x component and y component, you're going to get 0, and vice versa. And if you're going to multiply this term with this term, you're always going to get 1. So it has also unit norms, so it's not only orthogonal but orthonormal as well. As a consequence, R is an orthogonal matrix, meaning that R transpose R is equal to identity matrix. If both sides of 2.4 equation group are post multiplied by the inverse matrix R inverse, the useful result is obtained. So if you want to take the inverse of rotation matrix, you just have to take the transpose. That is, the transpose of the rotation matrix is equal to its inverse. Further observe that determinant of this rotation matrix is 1 if the frame is right-handed. Frame is right-handed means the rotation you are going to have is based on right hand and is based on your right hand angle representation. So if you want to represent these angle rotations based on left hand, the determinant would be -1. The above defined rotation matrix belongs to the special orthonormal group, which we call as O, of the real M cross M matrices with orthonormal columns and determinant equal to 1. This group is called as special orthonormal group, and it has many interesting features which would if we get the chance we'd like to explore. Now elementary rotations. Now after this is the general idea of rotation matrix, and we are discussing here as the pose. Now consider elementary rotation. Suppose that the reference frame OXYZ is rotated by an angle alpha in this one. Okay? And let O, X bar, Y bar, Z bar be the rotated frame. Now the rotated frame is this one. The unit vectors of the new frame can be described in terms of their components with respect to their reference frame. So if you going to represent this X bar, okay, X bar, so how can you represent this? Number one, cos of alpha, and then in this direction you go to the then sine of alpha. So that would become X bar because this is a unit vector, so you're going to represent like this. In the same way, if you represent this Y bar, okay, with respect to this, first you go in this way, okay, and if you go in this way, this would become, okay, this would become cos of alpha in x form, and no, sorry, if you're gonna go this way, this is gonna be cos of alpha, no, minus sine alpha y bar with respect to so I just want to have some time to think about it. Okay, now it's clear to me. To represent this y bar unit vector with respect to this, first you go in minus sine alpha, okay, which is actually this one, parallel to this one. This is minus sine alpha, okay, and in y direction this is cos alpha. So you go this way, cos alpha, and then in this way minus sine alpha because it is opposite to this. And for z bar it's similar, 0 0 and 1. Okay, now elementary rotations is continued. Hence the rotation matrix of the frame O x bar y bar z bar with respect to the frame O x y z is this one. Cos alpha sin alpha 0 minus sin alpha cos alpha 0 and 0 0 1. So this one is going to be the unit vector of new frame in for x bar. This one is for y bar and this one is for z bar. In a similar manner, so this is going to be the rotation matrix. In a similar manner, it can be shown that the rotations by an angle beta about axis y and by an angle gamma by about axis x are respectively given by this rotation matrix. You can check it out. Interesting thing to note is this: for z, one is here. For y, one is here, and rest of the thing you need to know that the position is changed. Cos alpha, sin alpha. So cos alpha, and this is cos beta minus sin beta. So this position is has been shifted to here, and this position has been shifted to here. So cos beta and sin beta and cos beta. So this thing has also been changed. In a similar way, for x-axis, one is here. Okay. Okay. In view of 2.6 to 2.8, the rotation matrix can be attributed a geometrical meaning, namely the matrix R describes the rotation about an axis in space, needed to align the axis of reference frame with the corresponding axis of body frame. And it is also interesting to note that the elementary rotation matrices in 2.6 to 2.8, the following property holds, which is if you put minus theta, for example, if you are having angle alpha and you're having some matrix, rotation matrix, you're getting some R. If you put minus alpha, you all need to calculate the new rotation matrix. You just need to take the transpose, the last one. Okay? So it is equally useful, and it is equally applicable for all kind of rotation metrics like x, y, z. Now, representation of a vector. Consider the case when the origin of the body frame coincides with the origin of the reference frame. So you're rotating like this and origin is matched. Then a point P in space can be represented either as this way or this way. So we have so with respect to O x bar, y bar, z bar, so it is like this one. Sorry. Okay. So this if we represent this point P with respect to x, y, z, this is going to be px, py, pz, and if we represent this point P with respect to this frame, which is x bar, y bar, and z bar, we can represent this. Since P and P bar are representation of the same point P, so it is interesting to know that we can present this P as you know, the P x bar, P y bar, y bar, P z bar, and z bar. I'm sorry, these are the unit vectors, x bar, y bar, z bar. So these are the unit vectors. You can put things like that. It is called unit vector symbol. So in the similar way like this. So we can represent this P, and you can see that this is actually a rotation matrix. So you can represent P point in a new frame with rotation matrix and position in that frame. So the rotation matrix R represents the transformation matrix of the vector coordinates in frame O, which is x bar, y bar, z bar, into the coordinate of the same vector in the frame O. So you can represent if you know the point, and if you have the rotation matrix, you can calculate this point's position in this frame as well. So this we call represent a transformation matrix as well. Okay, in view of the orthogonality property 2.4, the inverse transformation is simply given by this one. So if you want to go from this to this frame, I mean, if you have a P position and you have rotation matrix and you want to calculate this P bar, and which is the position of the point P with respect to x bar, y bar, z bar frame, you just need to take the transpose. This is very important um, property, and that would save you a lot of time in computation. Now, representation of a vector. This is an example 2.1. Consider two frames with common origin mutually rotated by an angle alpha. Okay, so these are two frames, x bar, x frame, y frame, and x frame, y bar and x bar. Let P and P dash be the vectors of the coordinates of a point P. So this is point P, and expressed in the frame O and O x bar, y bar, z bar respectively, shown in figure. On the basis of simple geometry, the relationship between the coordinates of P in two frames is this one. So Px, right, so it's going to be Px is equal to Px bar cos alpha minus Py bar sin alpha. So you can verify it, right? Px bar, okay, at this point Px bar cos alpha and Py bar minus sin alpha, because it's going to be downward. Yeah. Okay, so we can represent this Px as Px bar cos alpha, which is Px bar cos alpha. It's going to be like here to here, and then because this is an extra amount, we need to subtract it, and this is gonna be equal to minus py bar sine alpha, which is equal to because it's gonna be in negative direction, so this is minus py bar, and in this direction sine alpha, so it's gonna be like this, minus py bar and then sine of alpha. So this one would be sine of alpha, and we're gonna subtract this. In a similar way, py is equal to px bar sine alpha. So this length is equal to px bar sine alpha, which is like this, sine alpha, and then we have py bar cos alpha, which is equal to from here py bar cos alpha, which is like this. Okay. Basically, it runs from here to here, so we add this one and this one, so we reach up to here. The pz bar and pz are the same because it's being rotated about z-axis, which points out of the paper. Therefore, the matrix 2.6 represents not only the orientation of a frame with respect to another frame, but it also describes the transformation of a vector from a frame to another frame with the same origin. Interesting thing to know. Now here are some points. A rotation matrix can be also interpreted as the matrix operator allowing rotation of a vector by given angle about an arbitrary axis in space. Let p bar be a vector in the reference frame O x bar y bar z bar. In view of orthogonality of the matrix R, the product R p dash yields a vector p with the same norm as that of p bar, but rotated with respect to p bar according to the matrix R. I'm going to check this out. Yes, that is right. Sorry, this is correct. So the product R p dash yields a vector p with the same norm as that of p dash, but rotated with respect to p bar according to the matrix R. The norm equality can be proved by observing that p transpose p is equal to like this, p bar transpose r p dash, and applying 2.4. Now, rotation of a vector. Consider the vector p, which is obtained by rotating vector p bar in the plane xy by an angle alpha about axis z. So this is rotate. This vector p is obtained by rotating this vector from here to here. Let p x bar, p y bar, p z bar be the coordinates of the vector p bar. The vector p has components like this, and we can represent these components for px in this same way, right? So it is easy to recognize that p can be expressed as p rotation matrix with respect to this p bar about the axis z, where Rg is the same rotation matrix as we described in equation 2.6. So here is a conclusion about rotation matrix. In conclusion, a rotation matrix attains three equivalent geometrical meanings. Number one, it describes the mutual orientation between two coordinate frames. Okay? Its column vectors are the direction cosines of the axis of the rotated frame with respect to the original frame. Number two, it represents the coordinate transformation between the coordinates of point expressed in two different frames with common origin. Number three, it is the operator that allows the rotation of a vector in the same coordinate frame. So we can have these three properties, three equivalent geometrical meanings of rotation matrix. So with this presentation, I conclude my today's lecture. Thank you very much for your attention. If you have any question, please ask.